Welcome to Ask and Learn.
We want to sketch the graph of y is equal to x over x squared minus 4. Now in this chapter they give us this laundry list of steps we should follow to sketch a graph, and one of the things we should always do for any rational function is to go ahead and factor the numerator and the denominator, since we need to be able to find any kind of holes or vertical asymptotes as well as our x-intercepts. So the numerator doesn't factor since it's just x, but the denominator is the difference of squares, so it's going to be x plus 2. I'm going to go and zoom in a little. X minus 2 and x plus 2 all over x. All right, now we can't cancel anything out, so let's go to the first step, which is our domain. Well, we know we need to make sure that our denominator does not equal to 0. So that's going to be at x is equal to 2 and negative 2. So the domain is going to be negative infinity 2, negative 2, union, negative 2 to 2, union 2 to infinity. Let me go ahead and drop this down. All right. The next thing they tell us to look for is our intercepts. So let's go ahead and find our x-intercept first. So x-intercept, well, that's going to be where the function is equal to 0, or y is equal to 0. So 0 is equal to x over x squared minus 4. And I'm not factoring the denominator because remember, no matter what we plug into the denominator, we can never make this equal 0. So solving for 0, we would just get x is equal to 0. And since x is equal to 0, well, that would also tell us our y-intercept would be at the same point. So y-intercept is also going to just be y is equal to 0. So the origin is our only intercept. The next thing they suggest we find is any kind of symmetry we might have. So rational functions aren't really known for being periodic. So what we want to check instead is whether the function is even or odd. And we do that, remember, by looking at f of negative x. So plug in negative x, we get negative x, and negative x squared is just going to be x squared minus 4. Now notice that this here is equal to negative f of x. So this here implies that we have an odd function, so we have symmetry about our origin. All right. The next thing we need to check for is our asymptotes. Now we know that the limit as x approaches, so plus and minus infinity of our function f of x, which is really just y. So since our denominator has the larger power, going back to chapter 2.6, this tells us we'll have a horizontal asymptote at y is equal to 0. All right, now we need to figure out our vertical asymptote since we just found our horizontal using that information. So the limit as x approaches, so we said our vertical asymptotes are going to be where our denominator is equal to 0. So x is equal to 2 and x is equal to negative 2. So let's start with negative 2. So negative 2 from the right of f of x. So let's go ahead and plug that in. So it's going to be negative 2 from the right of negative 2 from the right minus 2 times negative 2 from the right plus 2. So let me go ahead and scoot that over a little bit. Now, negative 2 from the right is still going to be negative. If I subtract, so negative 2 from the right is going to be negative again, and then if I subtract something, that's still going to be negative. And then if I do negative 2 to the right, that'll be something like negative 1.99, and if I add that to 2, it would be positive. So it's going to be overall positive, so that tells us that this should go to positive infinity. And we don't even need to do the same steps for looking for as we approach it from the left, because we know both of these are linear terms. That means they should have opposite behavior on either side. So just to save a little bit of time, we know that this here should go to negative infinity. And you could go through the same logic that we did in the step before, but just to save a little bit of time. All right, now the next thing we want to do is look at our other intercept, which is going to, or our other vertical asymptote, which is going to be as x approaches 2. So let's look from the right again to start. And so it's going to be 2 from the right over 2 from the right minus 2 times 2 from the right plus 2. And I'll need to zoom out a little bit. And using similar logic that we did before. So the numerator is going to be positive because slightly to the right will still be a positive number. Now, something slightly to the right of 2 will be like 2.001. And subtracting 2 from that, well, that would still be positive. And 2 from the right will be all positive numbers, so adding something positive will be positive as well. So this here will approach positive infinity, and using similar logic that we did before, we can find out that as we approach 2 from the left, this should be negative infinity. All right. The next step is we want to find our intervals of where this function is increasing and decreasing, and any kind of local maxes or mins. So this is steps 5 and 6, and I think they should just be combined into one step. So we want to find what y prime is. So let's go ahead and do that on another page. So we have y is equal to x over x squared minus 4. Now to take the derivative of this, we're going to need to use quotient rule. So quotient rule is low d high minus high d low all over the square of what's below. And the d's just represent derivatives. So going and filling that out, we will get the following expression. And x squared minus 4, and then we need to square that. Now the derivative of x is going to be 1, and the derivative of x squared should be 2x using the power rule, and then the derivative of negative 4 will just be 0. So that should be 2x. And we can go ahead and rewrite this as x squared minus 4 minus 2x squared all over x squared minus 4 squared. Then in the numerator, we should have negative x squared minus 4, and let's factor that negative out. And that will leave us with x squared plus 4 in the numerator over x squared minus 4 squared. Now, notice that x squared plus 4 will always be strictly greater than 0, and x squared minus 4 squared should also always be greater than or equal to 0. So that means, since we have that negative out here, this function will always be less than 0 or decreasing. So we'll go ahead and use that. So let's go ahead and write what y prime is real fast. Well, y prime was negative x squared plus 4 over x squared minus 4 squared. And we already said that this here is going to be strictly less than 0. So our interval of decreasing will be everywhere that the function is just defined. So it's always decreasing since y prime is strictly less than 0. So it would just be negative infinity to -2, union -2 to 2, union 2 to infinity. All right. And we have no critical values for this since the numerator can never equal 0, so the function can never actually equal 0, and our derivative is undefined at x is equal to 2 and -2, but those are not in our domain, so we don't need to check those for critical points. All right. The next step is we need to find our concavity. So concavity and any kind of inflection points. So that means we need to figure out what y double prime is. Actually, let me go ahead and move this to the side over here instead. So let's just go ahead and put a little barrier there. All right, so like I was saying, we need to go find what y double prime is first. So let's go over to here again and start taking the derivative. So y double prime. So we can factor that negative out front and then just apply quotient rule again. So we are going to do low d high. So x squared minus 4 squared times the derivative of what's above, which is x squared plus 4 minus, then in the opposite order, so x squared plus 4 times the derivative with respect to x of what we have in the denominator. So x squared minus 4 squared. And then all over what we have in the denominator squared. So x squared minus 4 squared, but squaring that would give us to the 4th power. And so don't forget this negative out here. Now, taking the derivative of each of these, well, x squared plus 4 is just going to be 2x. And to take the derivative of x squared minus 4 squared, we're going to have to use power rule and chain rule. So the derivative of the outside is first going to be 2x squared minus 4. And then the derivative on the inside is going to be 2x. All right. And just so we don't have to do all that algebra, when we simplify this, we should be left with 2x x squared plus 12 over x squared minus 4 cubed. All right, so let's go ahead and use that. Oh, actually, before we do that, let's figure out where this function is equal to 0. So again, the denominator can never equal to 0. So we don't need to worry about that. So we just need to worry about the numerator. Well, x squared plus 12 can never equal to 0. And we know 2x can. So we get 2x is equal to 0, or x is just 0. So this is one possible point of inflection. All right. So let's go ahead and write down that derivative, or second derivative we just found, which is going to be 2x x squared plus 12 over x squared minus 4 cubed. And just for the sake of brevity, to find where this function is strictly larger than 0, I already went ahead and solved that as well. So y double prime greater than 0 tells us where the function is concave up. And that's going to be on -2 to 0 union 2 to infinity. And y double prime being strictly less than 0, well, this tells us is going to be concave down. And this is just the rest of the missing interval from our domain. So -infinity to -2 unioned with 0 to 2. So we found that x is equal to 0 is a possible point of inflection. So let's go ahead and see if we have a change in concavity here. So to the right of 0, we will be concave down, and to the left of 0, we're going to be concave up. So this here tells us we do have a point of inflection at x is equal to 0. All right, now let's go ahead and actually graph this function. So we know we have our intercept at only the origin. We know the function is odd, so it should be symmetric about the origin. And now we can go ahead and plot our asymptotes. So we know we have an asymptote at x is equal to -2 and x is equal to 2. So x equal to 2, x equal to -2. And we have a horizontal asymptote at y is equal to 0. So we have no local mins or maxes from 5 and 6, but we know at 0, at x is equal to 0, we should have a change in concavity. All right. Now for our horizontal or our vertical asymptotes. So let's start there. To the right of -2, we said that this should be going to positive infinity, and to the left of -2, it should be going to negative infinity. And we also said to the right of 2, we should be going to positive infinity, and to the left of 2, we should be going to negative infinity. Now we can go ahead and start graphing. So I'm just going to start in this middle section. So we're going to start to the right of -2, and we need to go to our origin, and at that point it's going to switch concavity. So to the left of this it's concave up, but to the right it's concave down. Now to the right of 2, well, we have no points of interest, so we're just going to go until we hit our horizontal asymptote, and we will need to approach it from above, as we can see there. And now we can go ahead and go to the left of -2. We have no points of interest after that, so we're just going to go to our horizontal asymptote and approach it from below. So you could maybe plot some actual numbers to make it look a little bit prettier, but since we're just sketching it, I think this is a good place to stop.